we shall be continuing this subsection on training and optimization, but this time around with the logistic regression algorithm. We have seen previously that with the logistic regression algorithm, when given inputs, say x0, x1, x2, so actually here we have inputs x1, x2, but x0 is the bias, so x0 equals 1. When given those inputs, we multiply them with a weight, or in this case a bias. Here we multiply this with a weight, this with the weight. We add all these values up, and then we apply a nonlinear function. And generally we use a sigmoid function for logistic regression algorithm. So here our nonlinear function is the sigmoid function, and then we have an output which is going to be between 0 and 1. So we had this loss previously, which was -1 on m sum of y target log of y predicted plus 1 minus y target log of 1 minus y predicted. Let's now see how to obtain the partial derivative of the loss with respect to theta j, as we did with the linear regression algorithm. The partial derivative of L with respect to theta j is the partial derivative of all of this with respect to theta j. Now L equals to this, so we just simply replace here. And then, as we saw previously, the partial derivative of a sum is the same as the sum of the partial derivatives. So we have -1 on m, the sum from I equals 1 to m of the partial derivatives of this plus this. Now notice that we've replaced y I predicted with 1 divided by 1 plus e to the negative theta 0 x0 up to theta n xn, and that's because we're applying the sigmoid function on the sum. And we've seen previously the definition of the sigmoid function. Now, as we saw previously, we generally try to keep this theta j xj term aside from the other terms, since this is the term which actually matters the most. So here we have negative theta 0 x0, yeah, it's a typo, it's supposed to be x0, so theta 0 x0 plus all values except theta j xj, which is equals alpha. So we take all these values to be alpha, and then we have plus theta j xj, and then this is raised to the power -1, because obviously we have the rules of indices which we applied here. Now what we'll have to do is actually to find the derivative of this with respect to theta j, and same this way. Also, it should be noted that since we have the sum of these two, we could simply find the partial derivative of this with respect to theta j separately, and then the partial derivative of this with respect to theta j2 separately. Now with this, we have to apply a function in a function rule, but before applying that, we have to understand how to find the derivative when dealing with log functions. When dealing with log functions, the log of a function f of x, for example, the derivative of that function with respect to x is given as f prime of x divided by f of x. You could check out our calculus course for that. Now we have y I target times log of this function. So what we simply do here is we find the derivative of this function and divide it with this same function. So that's why obviously you have here the denominator, this function. You could also take this -1 and send this way using the log rules and make your work easier, but let's just go like this. So with this we have the log of this, then let's find the derivative of this function, since we've already put f of x down, or in this case f of theta j down. Okay, we have this function which we want to derive and multiply it by the derivative of all this function to the power of -1. Now let's derive this function which is found in this bigger function, 1 plus e to the negative, let's call off this lambda, all of this to the power of -1. Deriving this, we simply apply the rules when deriving exponential functions. When deriving exponential functions, we could take whatever we have at the level of the power, derive it, and then multiply it by that same function. So simply here, when deriving e to the negative alpha plus theta j xj, that's constant of I, since we with the I term, we have the derivative of this with respect to theta j is going to be xj, and then we attach the I because we're dealing with the ith term. So we have xji, which comes up here. Now, times this term itself. So we have this, which follows. And then all of this, so we've actually derived or differentiated what's inside here, and we've put it aside, which is this xji e to the negative alpha plus theta j xj of I. And now we'll multiply it with all this function, or the derivative of all this big function, to the power of -1. Now, deriving a big X to the power of -1 is -1x to the -2. And that's exactly what we have here. So this is our big X to the power of -2. Now, the -1 will cancel out with a negative, which we already had previously, but we didn't make mention of. Where exactly did that negative come from? Recall that when deriving this function at this power, at the level of this power, we had negative alpha plus, or negative alpha minus theta j xj. So actually the derivative of theta j xj is actually negative xj. So normally here we should have negative xj. But because when deriving this big function, we have -1 times all this to the power of -2, the two negatives cancel out and we have just a positive sign. So that's why at this level we don't put anything. So that's exactly how we have the derivative of this divided by the function itself. Now, moving to the next step, we have to derive this function and then divide it with itself. So here again we have 1 minus yit. Remember, t is target, so it's basically what we had from right from here. So we have 1 minus yit into x ji e to the negative alpha plus theta j xj, which is similar to what we had done already here. Now, basically what we're doing here is we're differentiating this function with respect to theta j. Now, the derivative of a constant 1 is going to give you 0, so that's why it's kind of like ignored. And then finding the derivative of this function is exactly the same as the derivative of this other function we had done here. That's why we have xji e to the negative alpha plus theta j xj, and then this function which follows 1 plus e to the negative alpha plus theta j xj, all of that to the -2. Notice also that we have a negative sign. The reason why we have this negative sign here is while doing this the differentiation, this negative here appeared. So in this case, we had a global positive. That's we had a negative times a negative, which gave us a positive. But here we have a negative times a negative times a negative, which gives us this negative sign. So this is the source of this negative sign, and then divided by the function itself, which is 1 minus this. From here, we move on to simplifying. So here again we have, or we could simply multiply top and bottom. So if we multiply this top with this to the power of 2, we're going to have 1 plus e to the negative alpha plus theta j xj, all of this to the power of -2, times itself to the power of 2. So it's going to cancel out. So if this cancels out, and then down we have 1 plus e to the negative, or let's call all this big X. So we have big X to the -1 times big X to the power of 2. That gives us this. It gives us simply big X. So in this case, we have yit xji e to the negative alpha plus theta j xj of I, all of that divided by 1 plus e to the negative alpha plus theta j xj of I. That's what we have from simplifying this. Now, we do something similar right here. We multiply top and bottom by this term. So we are multiplying all of this by a big X to the power of 2. And that big X happens to be 1 plus e to the negative alpha plus theta j xji. Now, multiplying top is going to cancel this term out, and we're left with only this. So we're left with this, which is here. And then multiplying the denominator, we have this minus this. So we have big X to the -1 times big X to the power of 2, which gives us big X. So that's what we have here. And again, simplifying, we could simply let this term, which is at this power, to be a beta. So we have alpha plus theta j xj given as beta simply. So we could let it to be beta. And so here we have beta, here we have beta, from here we have beta, from here we have better, and then here we have better. Now, multiplying top and bottom by e to the better on this side, we have this. Now this cancels out, and from this we have a new relation which can be seen very clearly. Now let's have e to the better times e to the negative better. It gives us a 1. E to the better times negative e to the negative 2 better. It gives us e to the negative better. So actually this is multiplied by this and this. So we have this, and then taking this, multiplying with this cancels out, and we're left with this times xji. So that's basically what we have. Now notice the denominators are now the same for this side and then this side. That said, we have yit xji e to the negative better, which is this, minus xji plus yit xji. We got this by taking this times 1 and this times minus this. So we have this. Now the negative sign changes the signs, and then divided by this. So since these two have the same denominator, we just basically join them together like this. And joining this together and simplifying, we have this new term, which you could see clearly by factoring out yit. So like here we could factor out yit, and here yit, or we could factor out yit xgi. So factoring this out, yit xgi into e to the negative b plus 1. So we have this plus 1, then minus 1 because we have negative 1 here. So actually if you multiply this, you're going to get back this. So we have all of this divided by this term at the level of the denominator. And then rearranging, we have xgi into yit minus 1 over this term at the denominator. So basically what we've done here is we've had this xgi, we've kept it here. We have yit times this. So we take this now divided by this, which gives us yit. Then now we have negative 1 divided by this, which gives us this term. Now notice that this term we are having here is better, and better basically is all this. So all this is better. So what we having right here is actually y pred. So here we have the y pred. Normally we were dealing with a negative right from the top, but then this negative goes away simply because from here we see that we have y target minus y pred. But instead here we've reversed it, and now we have y pred minus y target. So this gives us the partial derivative of L with respect to theta j. And if we notice, it's quite similar to what we had when dealing with the linear regression problem. Our next concept will be that of the batch size. So what is a batch size, and why is it actually important? Now consider this data set wherein we consider all the elements, like all the data points. So we have 1, 2, 3, 4, 5, 6. It means if we're dealing with all these elements at the same time when doing the training or when updating our parameters, then we are working with a batch size of 6. This is quite different from the stochastic gradient descent algorithm, where we actually go and work with only one data point at a time, like this data point. So we work with only this one data point at a time. Whereas for batch gradient descent, we work with the whole data set at a time. So when updating our parameters, theta j, as we saw previously, where we had theta j equals theta j, that's theta j previous, minus alpha times the partial derivative of L with respect to theta j, we're going to take that step of gradient descent and do it and work with all the data set at a time. So our x will be represented by all this data set. Now, for mini batch gradient descent, we kind of arrive at a compromise between the batch gradient descent and the stochastic gradient descent. So in this case, we could select, say, only 3 data points, as is in this case, and work with. So we could take only this, or we could select even 4 or 5 or whatever. But once we select 6, we're dealing already with batch gradient descent. Now, it should be noted that whether working with mini batch gradient descent, or stochastic gradient descent, the update algorithm actually remains the same or similar. So here, for example, if we have theta equals theta previous minus alpha on m into, using the formula we had previously, we had x transpose. Now, if we consider x to be this matrix gotten from this data, then we have x transpose having dimensions n, where n is actually the number of columns we have here, times the batch size. Remember, x is made up of, is a matrix of dimension batch size times n, where n is the number of columns. So in this case, we have x transpose, which is n times the batch size times x times theta. Now, what's x? X is the batch size times n, or that's the dimensions of x is the batch size times n. The dimensions of theta is n times 1, as we have seen already, and then minus that of y. Y is basically batch size times 1. So in this case, we have batch size times 1. So from here we can have batch size times 1. So all this gives us what? Batch size times 1, and then this is n times batch size. And rearranging again, we have n times batch size times 1, which gives us n times 1. So in the case of stochastic gradient descent, where our batch size is equals 1, signifying that we're actually updating our parameters by working with one data point at a time. So we take this one time, we update, take the next, we update, the next we update, the next we update, the next we update, and finally this we update. So we're going one step at a time, or one data point at a time. So that's why we call it stochastic gradient descent. Now in that case, we'll see that if this were 1, at the end of the day, we'll still be having theta equals, or n plus n by 1, an n by 1 matrix equals an n by 1 matrix minus alpha on m times an n by 1 matrix. So it won't change the way we'll update theta as compared to if we had a batch size of 6. So if we have a batch size of 6, meaning we're updating all this data set at a time. So in that case, we will simply have this data set updated at a time. Our batch size here, if we place here 6, we'll still have this n by 1 minus this n by 1. So it doesn't really affect, or it doesn't really change the way we compute or we update our parameters theta. Now let's look at how, when doing batch gradient descent, the loss versus number of epochs curve look like. Now, what is an epoch? One epoch happens to be complete whenever we've updated the parameters of our model based on all the data set. So if we update our value for theta based on only this very first point, then we can talk about completing an epoch. An epoch is only when we have updated theta based on this, 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 and based on this. So with batch gradient descent, to go through one epoch, we just have one step. So in that case, we just have to take all these metrics and then pass it on here, and then have new values for theta, and then we have one epoch. So that's kind of like the curve we generally have. So this is not always very smooth, but as compared to the stochastic gradient descent curve, it's kind of smoother and more refined, since the errors made, or there are fewer errors made when computing this partial derivative of the loss with respect to theta j. Now let's look at the case of stochastic gradient descent. With stochastic gradient descent, we tend to make many more errors when computing the partial derivative of loss with respect to theta j. So that's the reason why we have this up and down, up, down, up, down. So it's kind of like decreasing, but with so much noise. Now to update our theta, instead of working with x, we work with x from say an index b to b plus batch size. So let's take the case where b is actually equals 0 and the batch size is equals 1. So in this case, we're going to be having x 0 to 0 plus 1. That's x 0 to 1. Now we're kind of like using the Python notation here. So x0 to 1 is simply x0. So it's this first line, or this data point on the first row. So here we have x0 transpose times x0 minus, or times x0 times theta minus y, when our batch size is 1 and b equals 0. So we deal with the first data point. Now if b goes to 1, we're moving from 1 to 2, so we're working with x1. So we're dealing with the second data point, and then we'll keep on adding b right up to this end, and that's exactly how we update theta while moving from one data point to another. Now in the case of mini batch gradient descent, suppose we have a batch size of 2. So we'll be working with initially b equals 0. So if we have 0 here, we have 0 to 0 plus 2. So we have 0 to 2. So x0 to 2 simply tells us we're working with x0 and x1. So it's this first two data points we're working with, and similarly here. So we're having this first two data points transpose times the first two times theta minus y. So we're updating our parameters theta based on these two data points. Now when b goes from 0 to 1, we are moving from 1 to 1 plus 3, because our batch size is 2. So we have 1 to 1 plus 2, so 1 to 3. We see that we have actually we are going to be working with this data point which we've worked with already. So instead of increasing from b equals 0 to b equals 1, we're going to increase from b equals 0 to b equals 2. So in this case we have 2 to 4. So we're going to be taking this data point and this other data point. So that's exactly how we've worked with this mini batch, and finally this mini batch. Now if we have millions of data points, we could obviously increase this mini batch sizes, and generally the mini batch sizes are of the order 2 to the power of p. So this is chosen because to make good use, or to make the best out of GPU architectures, is always better to choose batch sizes as 32, 64, 128, 256, so on and so forth. So generally we take batch sizes or mini batch sizes of this size. Now in the case of batch size, that's in the case we're dealing with batch gradient descent, where our batch size is the whole data set. In this case we're going to be having, we only have one value for b, which is when it's at 0. So we have 0 to 0 plus the whole batch size. So that's going to give us basically x. So in that case we're dealing with x transpose times x theta minus y. So that's how we could look at this very clearly. So recall that we're having this gradient descent formula, and then the way we work with the algorithm actually depends on whether we're dealing with a batch gradient descent, mini batch gradient descent, or stochastic gradient descent. Now a question may arise, which is that of knowing whether to work with the batch gradient descent algorithm, the stochastic gradient descent algorithm, or mini batch gradient descent. Generally, while working with larger batches or with the full batch gradient descent, as we said earlier, it tries to, or it does better in reducing the error we get when we're finding the partial derivatives of the loss with respect to the thetas or with respect to the weights. So that's one advantage of working with the batch gradient descent. Also, when working with large batches, that is even a mini batch, but a kind of mini batch with a considerable number of batches, and considering that in practice we use this vectorized notation, we kind of make use of the GPU multi-core architectures to speed up calculations. So working with a batch size of, for example, 32 is going to help you speed up calculations such that you can achieve convergence faster than if we were to work with a batch size of 1, and we shall see that practically. Also, there are limits to the kind of or to the number of batches we work with. So suppose we have data points of say 1,000,000 in number, and that each of these have, for example, 1,000,000 number of columns. So we have 1,000,000 features here, unlike here where we just have this 1, 2 features. So suppose we have now 1,000,000 features. You'll find that it's going to be very difficult to store the value of X in memory if we're working with a full batch size. So storing all that in memory is going to be difficult. So generally we break this into mini batches. So we now understand why mini batches are very important. Whereas so we may fall in a case where working with a stochastic gradient descent algorithm kind of like doesn't use our processors as efficiently as with a batch algorithm. But with a batch algorithm, we can store all the data all the data set in our memory. So we arrive at a compromise or at a middle point where we kind of select a batch size which will not occupy all our memory and still help speed up our calculations. We've now seen how, with the aid of the gradient descent algorithm, we could update the values of the weights and biases such that the loss is minimized. And there is a parameter alpha which we have to always tune to make sure that our model converges or our model doesn't diverge. Now, selecting an appropriate value for alpha is very important, as we may have a problem where selecting alpha, for example, to be 0.001 is going to let our algorithm converge with time. But then, if we had selected alpha to be 1, it would have even converged faster. And generally, we try to save time doing training. So, this choice of alpha is one that's very important and actually depends on the problem you're trying to solve. And you kind of get more intuition about how to use it when you solve as many problems as possible. Now, it's not always the case that we have alpha to be fixed. While solving or when working with many machine learning tasks, we tend to use values of alpha which change over time. We shall look at some of these policies for the learning rate alpha scheduling. For the first, we could consider this policy where we have alpha equals gamma to the power of n alpha 0. Now, this gamma could be a number from 0 to 1. That's a number between 0 and 1. Let's say gamma equals 0.9. Now, n is a number of epochs. So initially, we have n equals 0 and we have alpha equals alpha 0. So this is the learning rate at the beginning before running or before going through the first epoch. Now, when n equals 1, that is after we've gone through the very first, or after we've gone through all the data points to update the parameters theta, and we're going to the second time, we have n equals 1, for example. In that case, we have 0.9 to the power of 1, which is 0.9. So we have 0.9 times alpha 0. So we see that alpha now drops by 10% because alpha is now equals its initial value times 0.9. And then when n equals 2, we have 0.9 to the power of 2, which is 0.81. So alpha drops by roughly 29%, or rather 19%, since it's now 0.81 alpha 0. So this is one learning rate scheduling policy we can implement so that as the number of epochs increase, we could decrease the learning rate. And we have seen already that doing this is kind of interesting because generally when we are approaching our global minimum points, the slopes of the tangents reduce. And since the slopes reduce, using very large or using relatively large learning rates isn't the best option, since it may lead to a case where our algorithm doesn't learn very much. Another learning rate policy or learning rate scheduling policy could be this one, where alpha equals 1 divided by 1 plus n gamma to the power of p alpha 0. N is the number of epochs, gamma is a parameter which we could choose, and p another parameter which we could choose. And then we have this other one where we have 1 minus n on L alpha 0. So n obviously is the number of epochs, and L is a parameter which we could choose. And finally we have alpha equals gamma to the power of the floor of n on L. Now this floor simply means if we have for example 2.3 is going to give us 2. If you have 7.1 it gives us 7. If you have 7.9 it gives us 7. If you have 13.2 it gives us 13. So the floor basically takes whatever number and takes the closest low integer. So here we have gamma floor of n on L times alpha 0. L is a parameter which we could choose, gamma a parameter which we could choose, and n the number of epochs. So that's some of the learning rate scheduling policies we could use. Also, it's important to note that this could be done manually. So while doing the training, after a certain number of epochs, you could manually choose a value for the learning rate. Generally, we could have, for example, have started with say 0.01, and then we can move to 0.001, and then to 0.0001. So those are kind of the policies we try to put in place to make sure that our algorithm gets the best out of the data we have. Now, sometimes we could start with a lower learning rate and then later on increase it and then come back to a lower learning rate. So these are cyclic learning rate scheduling policies, unlike these ones which are generally decaying learning rate scheduling policies where the learning rate is just decreasing. We could have a case where the learning rate could be increased. That is, we start with a low learning rate, and after we increase it, and after we reduce, and maybe after increase a bit and then reduce. So there are many ways we could do this learning rate scheduling policies.